In this video, we're going to talk about one-to-one functions and inverse functions. Okay, so it turns out that the special type one-to-one functions are important for which functions have inverses. So let's start with the one-to-one functions. So what does it mean to be a one-to-one function? So we say a function is one-to-one if any two different inputs, okay, or x values in the domain correspond to two different outputs. So those are the y values in the range. Okay, now another way to say that is if you have two different x values, so let's say x1 and x2, then f of x1 is not equal to f of x2. Okay, so any two x values go to different y values. Okay, so that's the idea. So for example, f of x equals x squared is not one-to-one. Okay, so this, we can give an example to say that it's not. So we know that f of 2 is equal to 4, but so is f of negative 2. Okay, and obviously 2 does not equal negative 2. Okay, another example is x cubed minus x. So if you could actually factor this. You can factor it even further. Okay, so if I look at where y equals 0, we know that f of 0 is 0. So when x equals 0, I get the y value 0. But I also do when x equals 1 and when x equals negative 1. Okay, so you can think about the graph here. Okay, so it's negative 1, 0, and 1. And the graph is going to look something like that for this one. So what happens is actually, look at this. This is the line y equals 0. So when y equals 0, the graph crossed 3 times. Okay, now if I look at the graph of x squared, which we all know, okay, so the example I gave was when y equals 4, so we intersected twice, negative 2 and positive 2. So remember that functions satisfy the vertical line test. One-to-one functions also pass what we call the horizontal line test, which works the same way. Okay, but horizontal. So what that is no horizontal line intersects the graph in more than one place. Okay, so if you find a horizontal line that intersects more than once, then it's not one-to-one. Okay, so that's why those two above functions are not one-to-one, whereas these functions are both one-to-one. So if you look at the graph of x cubed, which we should know, looks like that. If you look at any horizontal line, okay, it doesn't matter where it is, it's only going to hit the graph once. Okay, so that passes the horizontal line test. So therefore it is one-to-one. Okay, as does the graph of 1 over x. Okay, so 1 over x we know has a vertical asymptote and at x equals 0, and a horizontal asymptote at y equals 0. So the graph looks like that. Okay, so again, any horizontal line only hits one place. Now it's okay that this horizontal line never hits. Okay, that's okay as long as it doesn't hit. So it's possible that you never hit, but you just don't want to hit more than once. Okay, so it also passes. Now, what this means is that one-to-one functions can never have a max or min, right? Because if they did, so let's say I have like a little maximum here, then my graph has to look like that around it, which means that there is a horizontal line that hits twice. Okay, it doesn't even matter what the rest of the graph looks like. Okay, maybe it only does it for a minute. Okay, but there's going to be, and in fact, now that I've done that, I can even hit more than once. Okay, so it turns out that you can never have maxes or mins if you're one-to-one. Okay, now what does this mean for inverses? So let's think about inverses first. So basically what the inverse is doing is it undoes what the function does. So to define an inverse, we need an identity. So that's an element that has no effect under the operation. Okay, so we've seen identities and inverses before. So let's just think about an example. So if we're doing multiplication, okay, with real numbers, the identity is 1. Because when you multiply by 1, nothing happens. Okay, and then the inverses, we call them multiplicative inverse because we're talking about multiplication. The inverses are going to be the reciprocal, so 1 over x. So that's because when you take x and multiply by its reciprocal, you get the identity. Okay, so x times 1 over x is x over x, which is just 1. Okay, so that's our identity. And for x, this is the inverse. Okay, so we want something that works similarly. And every number except 0 has an inverse. Okay, if we're doing addition, then the identity is 0, because when you add 0, you don't get anything different. And the inverse is just negative x, because then when you have x plus negative x, you get x minus x, which is 0, which is your identity. Okay, so when we're doing function composition, we want a function that when I compose it, nothing's going to happen. Okay, so this function we call I of x, and it's just x. Okay, so that's all it does. So this is the function that sends every x to itself. Okay, so it's like the graph of it is going to be y, the graph of y equals x, so it's a line. Okay, now I want you to do this. So choose a function, it can be any function, and compose it with the identity on both sides, so like what we did in the last section, and see what happens. Okay, so you should get the same function back. Now, you can pick any function you want, but in the subsequent video, the function I'm going to use is going to be 2x over x plus 1. Okay, so just if you want to use that one, you can, but you don't have to. So, but that's the one I'm going to do when I do that example later. So then, when we compose a function with its inverse, so that's going to, we haven't really talked about that, but the result is going to be x. So basically, the inverse undoes whatever the function does. So when we put them together, f is going to do something, and then we're going to compose it with the inverse, and the inverse is going to undo all those things. Okay, so that's the idea. So let's formally define this inverse function. Okay, now it only exists for a one-to-one function. So for a one-to-one function, f, okay, each x value in the domain corresponds to exactly one y value in the range. Okay, so that's the definition for one-to-one. Okay, so then the function that sends the y values in the range back to their x values in the domain is called the inverse function. Okay, so if you think about it in a picture, okay, so we have the domain, okay, and the range, okay, and then f is one-to-one. So let's say that we have this point here is x. So f sends this to y, which is some f of x. Okay, so that arrow is for the function f. Okay, now the function f inverse, which I guess I should give you that notation. So the inverse, we denote it with f to the minus 1. That's going to take this y value and send it right back to that x value. Okay, now the reason why you need it to be one-to-one is because then you know where to send it back. Right? So there's no ambiguity. I can't say that word. But anyway, there's not two different x values that go to the same y value. So the inverse knows exactly where to send it back to. Now, be careful. F inverse, so f to the minus 1 of x, so we read that. I'm just going to write read as f inverse of x. Okay, so not f to the minus 1. It does not mean the reciprocal. Okay, so this is so for that, excuse me, for this one we would write f of x to the power minus 1. So notice where the minus 1 is, the placement is different. Okay, so there's these brackets. So you want to be careful. I mean, it is very similar, but the inverse is not the reciprocal. Okay. So this notation is reserved for the inverse, so we never use it when we're talking about the reciprocal. So then, as we mentioned previously, if I compose the two functions, okay, so this one here is f inverse composed with f of x, and this one here is f composed with f inverse of x. Okay, so the order switched. In both instances, you get x no matter what. So they undo each other. So these are special ones where the order that you compose them doesn't matter. You get the same thing. Okay, now I'm going to skip the first example and move on to the second example here. So if x squared, f of x is x squared, is the inverse function root x. So that is going to undo what the other one does. So let's think about this. So let's say that I do f inverse composed with f of x. So that's going to be f inverse of f of x. Okay, and f of x is x squared. So this is f inverse of x squared, which is going to be the square root of x squared. Now, is the square root of x squared equal to x? It's not. Remember, it's equal to plus or minus x. Okay, so that's why the answer to this is no. Okay, so f of x equals x squared is not a one-to-one function. Okay, so that's going to cause a problem. So for instance, if I wanted f inverse of 4, okay, it could be 2 or negative 2. We don't know. Okay, so if f is not one-to-one, then it has no inverse. If it is one-to-one, then the inverse exists and is unique. Okay, so how do we find f inverse given f? So the method, which we often call switch and solve, okay, so what you do is you set y equal to f of x, so y equals your function, and then you interchange the variables x and y. Okay, so what it means is you switch x and y, and then you resolve for y, and that's what gives you the inverse. So I'm going to skip number 1 and do number 2. Okay, so I'm going to rewrite this as y equals 2 over x minus 3 plus 1. Okay, and then I do my switch. Okay, so then it's x is equal to 2 over y minus 3 plus 1. Okay, and then I want to solve. So I'm going to subtract the 1 over. So I have x minus 1 is 2 over y minus 3. And then I can multiply both sides by y minus 3. So I get x minus 1 times y minus 3 is equal to 2. Divide by x minus 1. So y minus 3 is 2 over x minus 1. Finally, I add 3. So y equals 2 over x minus 1 plus 3. And that's my inverse. So f inverse of x is 2 over x minus 1 plus 3. Wow, that wasn't very good. Maybe I should write this flat. Actually, let's do it down here. So f inverse of x is 2 over x minus 1 plus 3. Okay, now this is assuming that the function is one-to-one, which it is for this one. So that's our inverse. So these steps all in here is the solve bit. Okay, so you switch and then you solve. Okay, I'm also going to leave example 3 for you to do. It's similar to the one we just did. Now, the range of a function is often hard to find. Okay, so determining the range is not always easy unless you have the graph. Okay, but determining the domain is easier. Now, one way you can find the range, so remember our picture, maybe I'll draw it again. So if I have the domain of f and the range, and I take a function, okay, the f function, I guess this is the domain of f and the range of f. The f function takes x to y, okay, but the f inverse takes it the other way. So that means that this is the domain of f inverse and this is the range of f inverse. So they actually switch. Okay, so what we're going to take advantage of is that the range of f is actually equal to the domain of f inverse. So if the inverse exists and you find it, then you can find the range of f by finding the domain of f inverse. So to find the range of a one-to-one function f, you can find the domain of the f inverse function instead, which is often easier. Okay, now again, I'm going to skip example 4 because you did that one. And let's do example 5 here. So here I want the range of this function, which again, not that easy to find. Okay, we could graph it, but it's going to be hard to do. So let's first find, well, we could find the inverse. Maybe I'm going to show you, I'm going to do this by finding the range. Okay, so to find the range here, we want y so that y is equal to 2x plus 1 over x minus 1 for some x in the domain. Okay, so for here, the domain is x not equal to 1. Okay, so for any x that's not 1. So what we can do is we can put y, we can solve for x in terms of y. Okay, now this is the same thing as the switch and solve, but we're not switching them. Okay, so what we can do is put x in terms of y. So that's going to be, I'm going to multiply by x minus 1 on both sides. Okay, and then I'm going to have to expand the y through. Okay, so that's xy minus y equals 2x plus 1. And then I want everything with x's on one side. Okay, and everything with y's on the with no x's, sorry, on the other side. So that's going to give me xy minus 2x is equal to 1 plus y. Now I can factor out the x. And now I can divide. So x is 1 plus y over y minus 2. Okay, now I can see that I won't, so these are all equivalent. So at this point, we can see, or maybe I should do this in a different color. So here we can see we would not be able to plug in y equals 2 here. Okay, so that means we couldn't do it here, which is up there. Okay, which means that I can't get this y value to be 2. And that's the only value that I can't get. So that means that the range is going to be y not equal to 2. Okay, now if you use the switch and solve method, and you found the inverse, which I would recommend that you do to make sure that it's extra practice, but you should get 1 plus x over x minus 2. Okay, and this one has domain x not equal to 2. Okay, so that's the range of the other one. So the x values that you can't put into the inverse are the y values that you can't obtain from the regular one. Okay, so that's two different ways, but I mean, maybe you can see, hopefully you can see that this method here is doing exactly the switch and solve method without the switch part. Okay, so we're just solving for the other variable because that tells you which y values are going to be hard to find. Okay, so that's sort of the idea. That's how you'd find the range without actually finding the inverse, but you're essentially finding the inverse anyway. Now, what does this mean for the graph? So if xy is a point on the graph of y equals x, f of x, sorry, then the point yx is a point on the inverse graph. So you flip the x and y coordinates. this corresponds to flipping across the line y equals x on the graph. Okay, so for this one, let's see. So I have the graph of, this is x cubed. Okay, so let's do this in y equals x cubed here. So we have the point 0, 0. Okay, 1, 1. And negative 1, 1. Sorry, negative 1, negative 1. Now the other ones, I mean, it's hard to find a point here. If you were at 1/2, so let's do that point here. So 1/2, this is going to be 1/2 and 1/8. Okay, negative 1/2 is going to be negative 1/2 and negative 1/8. Okay, so now what this is going to be is I'm going to switch all the x and y coordinates. Now these 3 points that had the same x and y coordinates are going to remain where they are. Okay, but now I'm going to have 1/8 and 1/2. So up here, and negative 1/8 and 1/2, negative 1/2 down here. And what is actually happening is this is the line y equals x. Okay, so what happens is the graph is just flipped over that line. So when I'm above that line, I'm now below that line. Okay, and when I'm above that line, I'm now below that line. So this is going to look like that. And this blue graph is actually, you might recognize it as the cube root graph. Okay, so those two are inverses of each other, and you can see the graphs are just flipped over that line. So I should label these points. Okay, so this one is 1/8 and 1/2. Okay, this one down here is negative 1/8 and negative 1/2. Okay, now I'm going to leave this one for you to do. Now here they want you to graph it on a separate plane. So what you want to do is the points it gives you, flip those and then draw the graph. Okay, now and then you can compare to the line y equals x and see what happens. So I'll leave that one for you to do. So that is how the graphs of the inverse functions work. So they're closely related. So not the reciprocal, not 1/. So like even here, the equations are very different, but they're undoing what the other one does.